so we have been doing properties of the dot product. Okay, so the main algebraic properties are these: commutativity, associativity, and the distributivity. So, which means that every time you do algebra with vectors, that involves dot product or addition of vectors or scale multiplication of vectors. There's a group of properties that you might not remember all of them, but you can use them implicitly, or explicitly that, or first explicitly that implicitly, as if whatever you are dealing with are just numbers and you're using the same rules or habits, customs of dealing with expressions, as long as numbers, as long as the expressions themselves make sense. So as long as you don't divide vector by vector and things like that, then you're okay. So you don't add vector to a number. Things like that are not allowed. But otherwise, all kinds of combinations of multiplications and addition of vectors will be handled in the exact same manner. So that is the point of these properties. So you don't have to do this all the time. We proved it once, and then now we can treat vectors of any dimension in just a manner that's very similar to numbers. Look at every expression. It looks exactly like the one that you know from the other numbers. Okay, and so now we just we can do the same with vectors. Okay, there is one more operation, that is the cross product of vectors, but we'll get to that later. I just don't want to put it here. And secondly, the kind of outside. So this is these algebraic properties. Okay, and so now properties that are more geometric, which is reveal the purpose of the dot product in the first place. It is called the normalization property. And the second one is the angles. So even though we did confirm that fact for some of the products, some of the vectors, as well as for dimension 1, but in general, the proof either is it purely trigonometric, just you use pretty much the sum, the difference formula for cosine. Okay, so or we can do it. Well, there's one more property though. One more property that I want to put here before we get to the angles again, and that property is it doesn't have a really good name. It is very simple. But tricky. Okay, so once again, if you think of these as numbers, this is very familiar, and that is the first version of this equation. Unfortunately, we can treat what we're looking at in 3 different ways. So number 1 is all numbers. Right, so 0 is a number, x is a number 0, and yet also a number. Then the second one that we discussed previously, that would be scalar multiplication. So 0 times x is equal to 0. Then, okay, so this is a vector, but it is multiplied by a number. And the output is a vector again. Yeah. So that's scalar multiplication, so also familiar from a long time ago. And yet we have now the third version. Okay, 0 times x is equal to 0. This time, both of these are vectors. So a dot product is the product of vectors. But the output is a number. It's just crazy. Okay, so and as I said, it looks exactly the same. Verification of the product is also simple, because 0 vector is simply the vector with all components equal to 0. Okay, so you just multiply, and certainly you will end up with 0. Also, so that just takes time to get used to, but the context is king. So you have to know what is that you're dealing with in order to understand what's happening. So what are the you hardly ever have an equation that is not being introduced. The items in the equation or computations are introduced ahead of time, and they are you are told what they are, or alternatively, if you are doing it, it is up to you. It is your responsibility then to say what it is in every single thing here is it stands for. Okay, so if you want to rely, I would not encourage that, but sometimes it does happen. It does happen when the extra notation is used for vectors. Either it is boldface or it is arrows above the letters to point out which one is a vector, which one is a not, which one is a number. So without the arrow it is a number, with the arrow it is a vector. Okay, so this one would be 0 times x is 0 vector. Okay, so I'm not sure it's working. Now, okay, so next is the angles. So angles again. Well, first of all, so we are talking about Rn now, from now on, as much as possible. And what is the meaning of an angle between two vectors in Rn? So say AB in Rn, vectors. Okay, so what is the meaning of the angle? There is no physical, there is no such physical place in Rn, and so as long as we have 3, we're talking about something that it can be experimentally confirmed. I mean, you can actually have two lines taken, coordinates computed, and then angle derived from our formula. Okay, so that is the reality that we can we test the mathematics with reality, if you like, or vice versa. You know, we derive mathematics from reality. Rn is an abstract space, so that also kind of out of the realm of possibility. So what is the meaning of the angle between the two vectors? Between vectors AB in Rn. And the answer is you don't want to really come up with some wild ideas. You just reduce the new problem Rn to a null problem, and that is actually not even R3, it is R2. So the answer is reduced to R2. Okay, 2 is enough. So once again, if I have vector A here, I'll have vector B there. So it's always, this is Rn, so we are trying to even visualize Rn, and we might be in trouble. All of these might be, the basis vectors. So this is a 7-dimensional space, best you can imagine. So 7 vectors sticking out, and they're all perpendicular to each other. And that's a 7-dimensional space, best we can tell. So this is on the same thing, and then in this environment we have 2 vectors with the same origin. So what's the meaning of the angle? It's very simple, as I tried to indicate. There is a plane. So if we start with this big space, n-dimensional space, then we limit our attention to a plane in that is inside of Rn. Okay, so the whole thing is still Rn. Okay, but this is R2. Okay, so in that sense, it does make sense geometrically. It's not that it's not even the matter that it is R2. The point is a plane. Okay, it's not just R2. We know that R2 is a plane, and so we can do all the geometry of Euclidean geometry from high school with these. And so the angles make sense, the lengths make sense, the same as they were, and then that's how we do it. Okay, so practically speaking, then what we invoke, suppose we are now within that plane. This is our plane now, and there is nothing else. So this is our R2, and we have our vectors right here. We don't have to do anything else. A and B. Okay, and Okay, so the angle. What Euclidean geometry should we use here? So find, say, alpha. Find alpha. How do you find angles in Euclidean geometry?
Use the cosine rule?
Cosine rule, law of cosines, if you want to refer that, law of cosines. So, I mean, there's a sine law, and there may be the other things that you can try, but remember, we know that we're doing dot product, and we know that there's a cosine somewhere will appear. We already know the answer. We already know the answer, or we just need to demonstrate that it is true. So the answer is, this is the answer, right here. So that's supposed to be the cosine. At the top, the numerator is the dot product, and the two magnitudes in the denominator. Okay, so we know the answer is going to be cosine of that angle, and then so we apply the law of cosines, which means simply that I'm going to be looking at a triangle like this. Okay, so A, B, and C, and the law of cosine says that C squared is equal to A squared plus B squared minus 2AB cosine alpha. That's the law of cosines. Okay, now I am translating this into the language of, so this is a triangle from Euclidean geometry, but each side now is reinterpreted in terms of the vectors. Specifically, so these are A, C, B, and C are not really, they are not sides, these are lengths. So let's be clear about it. So A, B, and C are the lengths of the sides of the triangle, so they will be the lengths of the vectors. So this is the length of vector A. This is the length of vector B, repeated twice to A, B, cosine alpha, which is what we're looking for. This is what we're trying to find. Okay, on the right, it's slightly more complicated. What is the meaning of C in terms of vectors A and B?
Is it A cross B?
No. No, cross would go like this, to the third dimension, like this, the cross product. No, it's, what is it? What is that?
It's either A plus B or B plus A.
It's the difference. The difference. That is actually quite an important point here. This vector is, let me plot it again. How do you even compare two vectors? Two vectors. We know that we can measure distance between points. So you can still tell when 2 points are close to each other or not. What do we do with the vectors? We subtract. We subtract two vectors, and that way we know that is the difference between them literally, and if we take its length, we'll know how close they are. We're not comparing it here or there. We're not comparing lengths. So the only way to compare two vectors that taken into account simultaneously the lengths and the angle is to look at the difference. Okay, so the difference, A minus B, is this. Yeah. Okay, so like I said, so then if you want to, that is coming. Very important for calculus itself is that the difference between two vectors is the length of the difference between two vectors is the measure of how close they are to each other. You can see that, I mean, when we start taking limits, you can imagine that if this is getting shorter and shorter, the two vectors are getting to each other closer and closer in both the magnitude and the direction. Okay, so there we go. Okay, so I put here then A minus B squared. Okay, So we have expressed everything. We could write the answer, as a matter of fact. It is fine just to write the answer in terms of cosine of alpha. Just solve for cosine alpha. But there is no dot product, and the formula is not what we were looking for. Remember, the formula is that fraction, so this is certainly more complicated than it should be. So the alternative approach is through using the properties for to simplify things. So let's do that. Okay, so I'm using one by one. I'm going to use first I'm going to keep the right-hand side, and I will going to do something to the left-hand side. First, I'm going to use the normalization property. Okay, so the a minus b magnitude squared is simply the it is simply the dot product. The dot product of these two vectors, so that's normalization, the normalization property. Okay, now, as I promised, I want to simplify, so I'm going to be using the distributive property, as if these are just numbers. Okay, so let's write out. So I'll have a dot a minus b dot a minus a dot b plus b dot b. Okay? Now, I'm using normalization property again. So I'm going to have, what's the first term?
Oh, just the magnitude A.
Squared, yes. Yes. And so is the last one? The v of b, magnitude of b squared. Okay, so that's the normalization property. And I'm going to also use for what's in the middle, I'm going to use the commutative property. So it will be 2a dot b. Yes. Plus. Okay, so now these two are equal to each other, right? So I can cancel things. Okay, so what do I have? These will disappear. This, a squared here, a squared there, b squared there. So I'm left with negative 2a dot b is equal to negative 2 magnitude a magnitude b cosine alpha. Okay, so and that is the conclusion, finally the conclusion about the meaning of simultaneously we're getting the new meaning of the dot product, and at the same time we're getting that formula, promised formula about the cosine of the angle. So a dot b is equal to 2, I'm sorry, there is no 2, magnitude a, magnitude b, cosine alpha, where alpha is the angle between vectors a and b. So if it is defined, so if one of the vectors is 0, then the vectors the angle between them is undefined, but then both the left-hand side is 0 and the right-hand side is 0. Okay, so once again, I could take cosine alpha, and I have that fraction that we have. Okay, so and I can compute then the angles just the way I did. It is practically speaking, it is quite a helpful tool, because let's just take a look at say as an example this. Find the angle between the diagonal of a cube and its side. The cube looking like this. Okay, and then I'm talking about diagonal. So it goes diagonally like this on one hand, and on the other hand I have this this one. Doesn't matter which one, by the way. It is symmetric, so the angle will be the same. That would take a stereogeometry, quite a lot of work with looking, maybe not a lot, but using a lot of trigonometry to get to this angle, which is this one. This is the angle. But fortunately, we don't have to do that anymore because we just look at the dot product. So cosine alpha is the dot product of these two vectors. So the numerator is will be, so it is simply say 1, 1, 1. No, the other one. 1, 1, 1 dot product with the side, which is, let's say we take 1, 0, 0. Okay. On the, if we put it the axes appropriately, if these are the axes, then the coordinates of those points will be 1, 1, 1, the diagonal 1 and 1, 0, 0 for the side. Okay, and then divided by the numerator, which is the length of the second one, will be square root of 3. 1, 1, 1, square root of 3, and the, well, I could just as well write it here. So it is, as I said, 1 squared plus 1 squared plus 1 squared, square root, and here 1 squared plus 0 squared plus 0 squared square root. And if I multiply, in the numerator I have simply 1. 1 times 0 plus 1 times 1 plus 1 times 0 plus 1 times 0 divided by square root of 3, square root of 1. So altogether I end up with 1 over square root of 3. Okay, so, well, what is the answer?
So arc cos inverse of cosine.
That's our arc cosine of 1 square root of 3. There's really not no nice answer, you know, measured in degrees and so on. Whatever that number is, that's how it works. So you certainly can find it with any accuracy you want if you have any calculation. And once again, everything is, that's the point, is that with the coordinates available, with the tools of the dot product and so on are available, we can carry out these computations because everything is pre-measured, and all we have to do is just do, all we need are formulas to solve any problem imaginable about the geometry. Okay, so what remains here is something that I've been alluding to several times, and that's the projections. Projections on one vector on another. Projections. So, in a sense, you can imagine that we already have all the vectors in space, Rn, but suppose the Cartesian system either is there or we are looking for another one, for whatever reason. So then there might be one reason, say I over here, so suppose I have my vector already available, so that's my vector A. And then I'm introducing a new vector, there is no coordinate system to begin with, but I am starting to introduce it. So, for example, I will introduce vector I in some arbitrary direction that is of my choice for whatever reason, because of the problem I'm solving. So then, so A given, I is introduced. So what do we do with it? Find naturally the ith component of A. Okay, so just as we did it in the usual sense when the space is defined very specifically like this, so this is I, so then for this case, for the old case, the answer is 2, right? So I, this is 1, this is 2, the coordinate with respect to I, component with respect to with respect to I is 2, the horizontal 2 i's appear here, then its component is 2, that's the answer. However, in general, maybe the I is expressed in terms of the old, coordinate system, Cartesian system. Okay, so what do we do? And the answer is the projection. So this is what it looks like. If so, this is my vector A, and this is my vector I. Okay, so what I'm supposed to do is to have somehow the axis continue the line along the vector I, which will serve as the Cartesian coordinate axis of the system. And then what I'm looking for is this, which is called the orthogonal projection. This one. Of A onto I. The length of, or not the length technically, but rather the how many times I fits into this projection will give you the coordinate or the component of A with respect to this new system of coordinates. So the point of why we want to do it, remember, just to refresh your memory, sloped motion on a straight slope or curved slope, so at every point there might be different slope. It could be also expressing simply different vectors in terms of some set system of coordinates that is replacing the new one. You can always, it's always a possibility that in your space there is more than one coordinate system, so you have to switch back and forth. Okay, so how it works then, and fortunately the problem is really not, well, first of all, you define it explicitly. So given a vector, or two vectors, and another vector, I don't know what to call it, I'll call it V, and another V in Rn. This one definitely we do not want to be equal to 0. Okay, then the projection, the orthogonal, technically the orthogonal projection. Because technically it is quite a possibility actually that your alternative Cartesian, which is not going to be a Cartesian system anymore, might not be orthogonal to begin with. That could be a two-dimensional system, and that will algebraically work out just as well. It's just more complicated. So it's possible to have a non-orthogonal system of coordinates. So orthogonal projection of A on V is a vector. Of A on B. Such that, well, first of all, it has to be parallel to V. So orthogonal vector is a vector P. Okay, so what about its, first of all, it's parallel to V, like on that picture. So that red one is the P we're talking about. And secondly, the projection is orthogonal, so this triangle is a triangle of 90 degrees. And okay, so what should we say about that? That's property number 1. What's property number 2 about the orthogonality there? What should we say about how do we express that in terms of vectors?
P dot A is 0 vector, or is 0?
No, before we get to actually orthogonality, so let's say P is orthogonal to something. What is it?
Oh, to V. No, to. I thought it would be or.
Well, we just talked about this a minute ago.
Oh.
P minus A. Right. P minus A minus P, it's all the same pretty much. So like this. Okay, so in other words, if the way, so this is P minus, so P, no, this one is A minus P, not that it matters. I guess I could just go down like this. So this is P minus A, the one that goes down. The arrow pointing down is actually better because it actually points out the projection, and the meaning of the behind the word projection is like shadows of objects. So imagine that is a surface, and then you have a stick like this, and the cast shadow of that stick, the green stick on the ground, will be that red projection. Okay. So these are orthogonal, and now we can translate both of these into the language of vectors and find it. So that's the definition, and it's often the case that it is given in these compact terms, so they're with a lot of behind it. So this is a lot of behind it, orthogonality, vector algebra, as well as orthogonality, all is hidden here. And then you do something to actually find it explicitly. Okay, so well let's write it out. So first property is P is unknown. P is parallel to V, which means that it is a multiple. That's what parallel means. Yeah, so it's simply CV. And the second one means that P I could actually probably hold on a second. I could put a V here. It doesn't make any difference. Since P and V are parallel, then I put V here, and that doesn't change it. Okay, so V is parallel to P minus A. Okay, and then so then what it means, we know from the dot product, it means that V dot P minus A is equal to 0. Okay. So from these two, we derive what we're looking for. I substitute the first into the second. What do I have? V dot CV minus A is equal to 0. I use the distributive property, so which gives me V dot CV minus V dot A equal to 0. Okay. And I'm using I'm going to use the associativity property to pull C out, and I'll have C V dot V equal V dot A. Hold on, where are you? Okay, so we are looking for C. We're certainly looking for P, but really, since we know the direction, we just want to express C. The C will be the component of P in terms of V. Okay, so in other words, right here. So how many I's do I need over there to go all the way to the end of P? And that multiple that we're going to find it from here by simple division finally. So V dot A divided by the magnitude of V squared. Okay, and then furthermore, the formula is slightly longish, but oops, not that. For completeness, we want also to put the make the expressly state what P is. It is C times V, which is V dot A divided by magnitude of V squared times V. Okay, so that's the second part. So if P is the projection of A onto V, then P is equal to CV, and these are two properties are satisfied. So that's how we find C through this operation, and we find V as well. We will find P as well as well. Okay, so this expression certainly a bit challenging to parse because it has all the operations, a lot of operations that we just defined in one place. So this is a vector. It is multiplied, however, by a number. So once again, this is a vector, but this is a number. The whole thing is a number, and it is made of numbers because the denominator is definitely the magnitude squared. It's number. The numerator is the dot product of two vectors, which is also a number. So that's what it is. Looks more complicated than it is. And here you can see how it works out. It's certainly proportional to A, right? So that naturally to be expected. On the other hand, what happens if you increase the size of B? Well, it is actually inversely proportional to the size of B. Okay, so that will all come up a lot in what we are about to start, and that is the study of parametric curves, the calculus of parametric curves, and they are all determined by directions. And directions are given by vectors. Well, the parametric curves are vectors to begin with, even though they could be points. And then the directions certainly are given by vectors. So that is inevitable. So, okay, so the topic is the calculus of parametric curves. So we will have more examples. I mean, we've had a few, but not too many. Straight lines for the most part, like the parabola and the circle, as well as shifted circle, stretched circle. And we will going to produce more of them, and then we're going to study them. But let's start with the simplest concepts that we are, the simplest curves that we have as examples to begin with. And now it is a big topic, but considering that almost every single topic in Calculus 1 would have to reappear. Okay, so we have less than a month to cover all Calculus 1 issues with parametric curves. Okay, so starting with, let me write what the parametric curve is, just in case. So P is a parametric curve. Means that it is a function of a single variable, and the variable meaning the input, and a vector, a point, or vector variable. So in that case, so that's the output. Okay, so it could be P, depending on how you prefer to put it. P being a point in multidimensional space, or you can put it V, or any other name for it works out fine. Okay, so that's the output. Typically it is a T. P of T is equal to, let's just go straight to that example that we should appreciate so much, and that is the circle. Sine T cosine T sine T. That's typical parametric curve. And now we want to study them in the same manner as Calculus 1. So calculus issues. Well, here, what was the first issue in calculus? If you remember.
Differentiation.
No, that's the second.
Oh.
Limits. Before that, limits. So number one is limits, and then the derivatives. Yeah. So limits, and it is a function, so we can speak of limits. And as an example, I will be referring to what did happen in Calculus 1. So this is what in Calculus 1 must have happened. So you had some kind of function. Let me put it this way. So we're still speaking of limits. Okay, so this is y equal f of x. And what happened to limits? Say we would start at one point at a time. This is a. This is, say, b is equal to f of a. Okay, and then what we say is The limit, I'm not going to go into the definition too far, but at least let's just say what is that we're talking about, or did talk about. So f of x is approaching b, so that's y, as x is approaching a. Okay, so graph of a function on the xy plane, it might have a hole in the graph, and then the limit exists. We explain it in informal terms. This is very short, in a short way. So the y variable approaches the value of b right here as x approaches a. So let me maybe more of this. So say x is here somewhere. Well, maybe not like this. It's approaching. X is approaching a from say left and right, or left or right, or left and right simultaneously. And at the same time, x controlling y, and then what's happening is this is where what's happening to y. Y is approaching b. Okay, so that's what we're saying, or did say in calculus 1. Now, what is the difference? The difference is that the picture would be very much similar, but what's difference is that x and y are not dependent on each other anymore. So y does not depend on x. So that word as will disappear, because x might be approaching a number, y might be approaching a number. Does that fact have anything to do one with the other? Maybe not. Okay, so it is this time. It is we have a dependence of x on t and y on t. So it will be exactly the same, except I will write it this way. So except it will be like this. X approaching A and Y approaching B. Okay? It illustrates this, illustrated by the same exact picture. Right? So X is here approaching A, Y is approaching B. Picture has been described, and as you can see, there is no dependence of X on Y or Y on X. They're totally equal. And but we do have to point out what forces this to happen. It is the dependent variable that forces this to happen, just like it was here in calculus 1. The behavior x that we were able to control, we set x to a, and that made y go to b. Okay, so we are in a similar place here, except the independent variable is a t, and so t might be, once again, we're controlling the independent variable t, and we set it to some value t naught, which is, by the way, is invisible on this picture because that's the third variable in the third dimension. So what we're saying here, as t approaches t naught, so we are traveling in time through this curve, okay, and then what we're observing is, as time approaching some time of t naught, which is something special about it, what's happening is x is approaching a, y is approaching b, like this. And altogether, what it happens is, and now that's certainly what we care about the most is this. As time approaches t naught, our location approaches point AB. Okay, so if I just want to rewrite this, so this is for parametric curve now. This is calc 1 that we started with, now parametric curves. And but this is not good enough because we are concentrating and relying entirely on vectors, so or points, and we prefer to express it in terms of vectors. So not one coordinate at a time. See, that's what's happening there. One coordinate at a time. And then you have 3 dimensions. You have 3 coordinates at a time, n dimensions, n coordinates at a time. You have n lines like this. So instead, we're doing it vector-wise. So this is what it looks like. Then we have, let me start with this, x, y. Either it is, well, I start with let's start with a point. I will do everything in parallel. So if we speak of points, then we're saying xy is approaching AB as t is approaching t naught. Of course, x is a function of t, y is a function of t. That's what we're talking about here. And if we want to prefer vectors over points, which is common, then this is the notation. So we are talking about then okay. So that's what we're saying. Once again, x, it is in fact not, it is location, but at the same time, it is each of these is dependent on time. Okay, so then we have to know now before we move on that this is not you cannot really easily express this in terms of that. This in terms of that. So x approaching A and y approaches B is not really, you have to realize that it's happening simultaneously. So x has to approach A at the same time as y approaches B. You cannot do one or the other. They have to approach simultaneously, and that would then literally would mean that what we're seeing over there, that point over there in red, this is point xy, and it is approaching the point, the circular point over here, this point, and this point is point AB. Okay, so we have to just to say what it means for one point, for one vector to approach it, approach another, and it's all about naturally about the distances. So for the former case, it is the distance between. It's even harder to write it in. Let me go for vectors for the multidimensional notation right away. So I'm saying that P is approaching, say, A as T approaches T naught, or if we prefer vectors, V is approaching vector A, or whatever the name of it is, as T approaches T naught. Okay, so this is preferable because now we have abandoned the idea that there must be a Cartesian system there to begin with. Instead, we just speaking of points and vectors as if they exist independently. As long as we have all of the tools that we have been talking about, we can handle those arrows. And the arrows indicate nothing but limits. And all we have to do is just to explain what it means for a point P to approach point A. What does it mean? The meaning is very simple. It is simply the distance between them is going towards 0. So dPA is going to 0 as T goes to T naught. Okay, so A is fixed. Naturally, P is depends on time. You're moving through space, whatever dimension is. You measure the distance as we have, or compute the distance through coordinates or otherwise, and that distance has to go to 0. So as that picture might be. You can approach it in any weird way. So if this is A and this is P of T, it might approach the point in any way you can imagine. So one more thing is, what is the second one? How do we handle this convergence? One vector to converge to the other.
The magnitude of the difference.
The magnitude of the difference. Remember, we just talked about it a long time ago. So V minus A minus U, once again approaches 0 as T goes to T naught. So that looks, it's harder to express like this, but you can imagine how this is my vector U, and vector V is trending towards it like this. So it rotates simultaneously as well as getting its magnitude appropriately shortened as well. Okay, so we'll continue next time with this.